going to speak about family of long-range models and the collective behavior of a family of particles that are interacting with long-range interactions and their dynamics. And I would also like to thank DST for very generous funding, without which this work would have not been possible. So the contents of my talk are as follows. So before that, this work has been done. Several parts of this work has been done with various collaborations. Avanish Kumar, who was a visiting fellow here, and my colleagues at ICTS, Abhishek Dar and Anupam Kundu. Sana Agarwal, who was a visiting student and now is at UC Boulder, Satya Mujumdar, Gregory Sher from Paris, David Mukamel at Weizmann, Banu Kiran, who is a student here at ICTS, and David Hughes at Princeton and IIS. So most of what I'm going to speak is going to be in these three works. And so basically, the contents of my talks are as follows. So I will start with some brief definitions, statements, and questions. I will give some background motivation of why we are doing this work. And then I will present some, basically give a flavor of some results of collective description of interacting systems. Basically, it's a description instead of tracking individual particles. The question is, can I give a collective description for a lot of particles? And then I'm also going to speak about some dynamical properties like out of time ordered correlators, and then I will conclude. So basically what I will focus on here is a bunch of particles which are given by these blue circles here, which are trapped in an external confining potential, okay, which is Vx here, and in which the particles are all interacting with each other by some repulsive potential. So the particles are trapped in some external confinement, and on top of it, they are also interacting with each other. And every particle is basically interacting with every other particle. So it's a very long-range system. And then the question is, how do these particles settle down? What is their collective density, and what are the properties of such systems? So basically, let's say at zero temperature, it is clear that there are two competing things. One is the particles are all trapped by this external potential. So you can imagine keep putting it in a bowl. So the bowl doesn't allow it to fly out. So there is that external potential. And at the same hand, the particles cannot come too close to each other because they are repulsive. So on one hand, they are unable to come too close to each other. On the other hand, they are unable to go too far from each other. So there is this very intricate competition between these two. And the question is, how do they settle? So this is already at zero temperature. At finite temperature, there are these additional complications due to entropy, where entropy and external potential and repulsive interaction all start playing a very complicated role. So my goal for this talk is going to be to ask, what is the density of particles? So naively, you can imagine that because of this external trap, let's say you have a harmonic trap, that there are more particles at the center. And there are less and less as you go to the edge, because you have put them in a harmonic trap. So naively, the density would be like a dome, because you can think of density as just 1 over interparticle distance. There are more particles in the bulk, and as you go to the edge, there are less and less particles. So the density will be like a dome. Okay, so now the question is, so for most of my talk, this is the bolded red box here is what you should focus on. So there's an external harmonic trap, x square. So it's like a harmonic potential. And then there's a repulsive interaction where every I and jth particle is interacting with some power law interaction. And K here is basically the strength of the power law. Okay, so now the question is, why do we care? It turns out that this family of models that I have boxed here is very ubiquitous in nature and has various examples. So for example, if let's take k equal to -1, then that is known as the one component plasma. So you see that particles are in a trap and they are repulsively interacting as xi minus xj. And it turns out that the density of this kind of system is essentially flat. So the particles are neither too close to each other nor too far. They all happen to become equally spaced. Now, this is a very non-trivial finding because it is not very obvious just by looking at the energy to say how these particles settle down. If I take k equal to 0 slowly, carefully, then I get the famous Dyson's log gas. So all I am doing is I'm just taking this boxed equation here and taking various values of k just to show how relevant this kind of family of models is. So if k equal to 0, then it is well-known Dyson's gas, log gas, and there it turns out that the particles are arranged in such a way that their density eventually forms a semicircle known as Wigner's semicircle. And these particles precisely sit at zeros of some Hermite polynomials. So there is a lot of mathematical structure to this, and this is also relevant for, in random matrix theory, Kartar-Pai-Zhang, universality class, and so on. Now, if I take k equal to 2, this is known as Calogero-Moser system, which is a very interesting system in itself. It is integrable even in external potential, and so it is an integrable model, and it has various. It appears in various branches of physics and mathematics. So therefore, one can ask, for general k, what is the density of such a system? And I just gave you sample examples for some values of k, and it turns out that for many other values of k, you have a series of very relevant models that come in physics, chemistry, especially in cold atomic systems, ions, and so on, which I have shown here. So for various values of k, you have various physical examples. So therefore, and not only such things, but also the fact that you can do absorption imaging and actually measure these densities, and these cutting-edge experimental technologies in cold atomic systems makes these questions quite important. Okay, so once you know such a collective description, you can also study how these densities evolve in time. So that is another interesting question, which makes these kind of investigations important. Okay, so now let me just go to the answers. So it turns out that for arbitrary k, we computed the density, the collective density of such a system, and the collective density basically takes this dome kind of shape, which is given here. So we can calculate various properties of this density function. And this is an exact result in large n. So this is a field theory result for assuming that you have large number of particles, which is physically very relevant because some of these cold atomic systems have very large number of particles. So this is a good limit to study. And we see that there is exact agreement between our analytical results and brute force numerical calculations of how these particles settle down for various values of k. Density is a macroscopic quantity, and it comes by minimizing some collective field theory, which is given here. So basically what we find is that for different values of k, the whole system of let's say 100 particles or 200 particles, this whole microscopic system can be written as an effective collective theory of densities. So this is basically one of our findings. Now the question is, I told you till now that every particle was paired with every other particle, but then one can ask, what if every particle is paired only with some d number of particles to its neighbor? So which is experimentally quite relevant because of screening effects. So the 7th particle may be coupled to 8th particle, 7th particle may be coupled to 9th, it may be coupled to 10th, but it sort of doesn't couple to 11th because it is too far. So that generalization actually brings in a lot of interesting physics, where we restrict that these particles cannot be coupled all to all, but they can couple to d number of particles to their neighbor. And we find that because of this, there is a very intricate computation between interactions and entropy, and we found results for different values of K. And as I was saying, different values of K remind us of different physical systems. So once you know such density behavior, you know a lot about the system, because instead of tracking all these 300 or 400 particles one by one, I can track just the density field. And it turns out that we get very non-trivial results depending on the value of K. So and we can study a situation where we have not only harmonic trap. Till now I presented harmonic trap, but one can have like a box-like potential, and over the past decade or so, box-like potentials have become very important in cold atomic systems, where box-like potentials are reasonable, quite homogeneous in the bulk, and they suddenly become sharp. So that is has been also realized in cold atomic systems and so on. And we can study a variety of interactions. And these have also been verified by brute force Monte Carlo numerics, where we see that microscopic calculations actually match our macroscopic density. And just to summarize the collective description of these models, one could say the following: if you have just finite finite range interaction, then we show that when K is greater than 0, the interaction dominates. When K is going to 0, both interaction and entropy dominate. And when K is less than 0, only the entropy dominates. So this is a model where you can see the effects of entropy and interaction coming together, which is usually very difficult to bring them on an equal footing. And when you have all-to-all coupling, like the one I showed here, there you can see that that for large K, your collective description is a local theory. Notice that all particles are coupled, every particle is coupled to every other particle, but the collective description actually turns out to become local if K is large. And if K is less than 1, it becomes non-local. So the take-home message, broadly speaking, is that instead of tracking individual particles, which is often very difficult, and we are often interested in collective behavior, we don't care too much what happens to 70th particle or 85th particle, but we care more about what is the density and how does the density evolve. That is the kind of questions for which this is a starting step. So till now I did not speak about time dynamics. Then one could ask, what are the dynamical properties of these kind of systems? One of the most interesting dynamical properties or dynamical questions would be something called out of time ordered correlators. So which basically tries to study spatio-temporal spread of perturbations. So the idea is the following. So this is the same model that I had shown you, with the only difference that we have a kinetic energy term. So now suppose I ask this question. Let's say I start with 2 copies of the same system, and I start with identical initial conditions, absolutely identical initial conditions, and I only change copy B by the middle particle of copy B by epsilon. So they are almost same initial conditions, but the only difference is the middle particle of the second copy is slightly different initial condition. So, and then I calculate how these initial conditions start evolving in time, and how this deviation spreads both in space and time, because this is so I have chosen a one-dimensional system, and I can ask how these differences grow both in space and in time. Okay, so these are our results, and we can see that initially it's a delta function, and then it basically spreads both in space and in time. They have very interesting properties. Okay, so this is my last slide. So basically, if you start with almost same initial conditions, and then you can think of making a light cone. And this is basically the light cone we are picturing, and this is a light cone for a particular value of K. So this basically says, how do perturbations spread in space and time. And if you are inside the cone, then you can differentiate between integrable systems and non-integrable systems. If you're outside the cone, you can differentiate between long-range systems and short-range systems, and so on and so forth. So this is basically a very interesting property of this system. And our family of models has both integrable and non-integrable cases. So the key findings for these are that we have exact analytical expressions for the OTOC. We have dispersion relations. We have studied butterfly velocity asymptotics, and we can study this entire dynamical properties also by a field theory approach. And properties of chaos and non-chaotic behavior and so on. So just to conclude, basically I have explained some collective description of long-range systems. There's a striking difference when all particles are coupled to all other particles, as opposed to all particles coupled to just few of their nearest neighbors. There's exact agreement between numerical and analytical results, and I have explained the spatio-temporal spread of perturbations at low temperature. And these are some of the open questions: high temperature, integrity versus chaos, nonlinear hydrodynamics, connections with experiments, and so on. I thank you for your attention.